Okay, so let's look at the integral 1 to 3 x cubed. So a graph is not necessary, but I'm going to draw a graph for most of these examples to emphasize to you that these integrals represent areas of certain regions, right? So what area does this represent? Well, draw the function, right? So here's y equals x cubed. And we're on the interval from 1 to 3. So here's 1 and here's 3. So we are looking at this region, right, under the graph of y equals x cubed. Now, how do I actually compute this thing? What did fundamental theorem of calculus part 1 tell us? So I just spent like 20 minutes going over the theoretical background, and so that wasn't for you just to kind of not pay attention. So what does fundamental theorem of calculus part 1 tell us how to calculate this integral, or what can we do to calculate this integral?
Take the antiderivative of.
Okay, so give me one antiderivative, Thomas.
It would be 3x squared over 2.
That's derivative. 3x squared would be the derivative, right? Antiderivative, you have to go up a power.
Oh, right. 3x to the fourth divided by 4.
X to the fourth over 4, right? Increase the exponent by 1 and then divide by the new exponent. Let's see if a few people in chat have written it all out also. Okay, so you find an antiderivative and then you substitute the two numbers, right? The limits of integration, right? The 1 and 3, they're called the lower and upper limit of integration. So I substitute the top number, 3 to the fourth over 4. I substitute the bottom number, 1 to the fourth over 4. I do this arithmetic and I should get what? 80, right? Or 20 actually. 81 minus 1 all over 4, so I get 20. And that's it. Right? No Riemann sums, no geometry, no nothing. Okay, so I'm going to give you a few to look at. Okay, so look at these. So for these two, part D and E, try not to use the fundamental theorem of calculus. You're allowed to use part C. You're allowed to use part B or part C. You can use previous results, but do not use fundamental theorem of calculus a second time for D and E. So I'm going to give you a few minutes to do that. Let's say 3.5 minutes to get as many of these done. Caleb, you got everything?
Yep.
Hmm. Mohammed, you slided? I see you typing and scrolling.
Yeah, I was using Desmos to graph them.
Oh, using Desmos. Oof. Is that cheating? Okay, so let's look at this. Do you really need to graph it though? I mean, if you're curious, that's fine. We don't really need to graph it. Okay, so let's graph this. And you don't, this is not necessary part of the solution, right? You can compute this integral using fundamental theorem of calculus without a graph. But I like to graph it just to keep on emphasizing that these things are areas of regions. So secant squared, or secant has asymptotes at negative pi over 2 and pi over 2, right? Because that's where the cosine is 0. Okay, and the graph looks something like this. Doesn't look symmetric. It's supposed to be symmetric, right? Okay, so here's pi, negative pi over 4. Here's pi over 4. So I am getting that area. Okay, so let's actually compute this using fundamental theorem of calculus. So what was your first step here? Yeah, find the antiderivative, which is what? So fundamental theorem of calculus tells you get the antiderivative and then substitute the top number minus substituting the bottom number. And so Justin says the antiderivative is tangent of theta. So I substitute in negative pi over 4 and pi over 4. Okay, good. So I get tangent of pi over 4. Actually, let's put this on the next line. So I get tangent of pi over 4 minus tangent of negative pi over 4. So in other words, I get 1 minus negative 1, so I get 2. Okay, next, sine theta from 0 to pi. So I'll leave that on the screen for a second. So again, let's look at the graph of this. All right, so here's pi. Here's going to be 2 pi. Okay, so if I'm just going from 0 to pi, I'm actually just getting that area right there, that shaded area. Okay, so again, fundamental theorem of calculus. So we get an antiderivative of the function first. So who wants to give me an antiderivative of sine theta? Negative cosine theta, right? Make sure you have that negative. I mentioned this before when we did section 4.9 with trigonometric functions. Always make sure you can have double check. Now, be careful here with, we're going to have a lot of negatives, right? We get negative cosine of pi and then minus negative cosine of 0. So we get negative, negative 1, right? We get negative, negative 1 minus a negative 1. Right, so just make sure you get everything. So you get 2 there. So you have a lot of negatives. Make sure you keep track of all of them. Now, for the other two, I actually said, don't use fundamental theorem of calculus. Of course, you can use fundamental theorem of calculus. Fundamental theorem of calculus will do everything for you. Just put that down over there. Okay, so we have the same function. Zoom out a little bit. Except now I want this total area. Now, it's actually not the area I want, right? It's the net area, right? Because we know that integrals represent net area. So what would be the answer to this without using fundamental theorem of calculus? What would you say? 0, right? Because these two regions, the two humps from 0 to pi and pi to 2 pi are congruent to each other, right? So the area cancels. Now I will stress here that if you wanted to use fundamental theorem of calculus, you can. The fundamental theorem of calculus, you do not have to worry about any of that. Oh, is it above the x-axis? Is it below the x-axis? First of all, you would still get the same antiderivative, negative cosine theta. And when you plug in the two numbers, I get negative cosine 2 pi minus negative cosine 0. But cosine of 0 and cosine of 2 pi are both 1. So you just get here 0. So the fundamental theorem of calculus kind of works that out for you, right? So it knows, it kind of snuffs out the area. It knows that the area is below the x-axis, and it figures out that the whole thing is 0. So you never have to be clever if you don't want to be. Now, what about from 0 to 3 pi? How did you do this without fundamental theorem of calculus? What did you say for this? Said 2. So if we extend, if we keep on going to 3 pi, right? We know that the sine function is periodic, right? So we're getting all this stuff. Now we know that each hump has, right, here's +2, that's +2, but then we know that the area below is -2, right? Someone says same as part C, right? Exactly. 2 of the humps cancel each other out, but the third hump gives me just +2. And again, you can use fundamental theorem of calculus. It'll figure that out for you. But if you already have the result, if you already have the result that from 0 to pi, it's 2, we know that from 0 to 3 pi, it's also 2. Okay.